Deep in the void between stars, something lurks that defies everything we think we know about matter. Not black holes, not neutron stars, something far more subtle, far more alien, and in many ways, far more terrifying to physicists. It's a cloud so cold that the very concept of temperature begins to lose meaning. A cloud where molecules move so slowly that quantum mechanics takes over from classical physics. A cloud where time itself seems to stretch into eternity. These are the cold CO clouds, and they're about to shatter your understanding of reality. Right now, as you listen to this, there are regions of space where carbon monoxide gas has cooled to temperatures just a few degrees above absolute zero. We're talking about minus 270 degrees Celsius. At these temperatures, something extraordinary happens. The random thermal motion that defines what we call heat essentially stops. Molecules that would normally be vibrating, rotating, spinning in countless chaotic ways suddenly fall silent. They enter states that shouldn't exist according to our everyday experience of the universe. But let's step back for a moment. What exactly is absolute zero, and why does approaching it unlock such bizarre phenomena? Absolute zero is the theoretical temperature at which all molecular motion ceases. It's minus 273.15 degrees Celsius, or 0 Kelvin on the absolute temperature scale. It's not just cold, it's the absence of thermal energy itself, the ground floor of temperature, the basement of the universe. Here's the thing though, you can never actually reach absolute zero. This isn't just a practical limitation, like saying you can't travel faster than light because you'd need infinite energy. No, this is a fundamental law of thermodynamics. The third law, to be precise. It states that reaching absolute zero would require an infinite number of steps, an infinite amount of time, an infinite investment of resources. The universe itself forbids it, and yet we can get terrifyingly close. In laboratories on Earth, scientists have cooled atoms to billionths of a degree above absolute zero. But nature got there first. In the vast molecular clouds scattered throughout our galaxy, carbon monoxide has been cooling for millions of years, radiating away its energy into the infinite heat sink of empty space. These CO clouds are found in the darkest regions of the cosmos. They exist in giant molecular clouds, the stellar nurseries where new stars are born. They hide in the shadows of dense dust lanes that block visible light. They drift through the interstellar medium like frozen ghosts. Carbon monoxide might seem like a strange molecule to focus on. After all, hydrogen is far more abundant in the universe. But CO has a special property that makes it invaluable to astronomers. It has a small but measurable electric dipole moment. This means that when CO molecules rotate, they emit radio waves at very specific frequencies. These radio signals can travel through the dust that blocks visible light, allowing us to peer into regions of space that would otherwise be completely invisible. The most common emission line from CO occurs at a wavelength of 2.6 millimeters, corresponding to a frequency of 115 gigahertz. When we point radio telescopes at dark clouds in space and tune to this frequency, we can map the distribution and motion of cold gas with extraordinary precision. But the temperature of these clouds tells us something profound about the physics of the cosmos. When astronomers first measured the temperature of interstellar CO in the 1970s, they found something unexpected. The clouds weren't just cold. They were colder than they had any right to be. Some regions showed temperatures of just 10 Kelvin. Others drop to 7 Kelvin. The coldest known molecular clouds in the universe clock in at around 3 to 4 Kelvin, barely above the cosmic microwave background radiation that fills all of space. 3 Kelvin. Let that sink in. That's 3 degrees above the absolute floor of temperature. At these temperatures, CO molecules are moving at roughly 100 meters per second. That sounds fast until you realize that at room temperature, air molecules zip around at 500 meters per second. The cold slows everything down. But the slowing isn't just about speed. It's about quantum states. Every molecule can exist in multiple quantum states. Think of these like rungs on a ladder. At high temperatures, molecules have enough energy to jump between many rungs, occupying excited states of vibration and rotation. But as temperature drops, they fall down the ladder, settling into lower and lower energy states. At temperatures near absolute zero, almost all molecules occupy the ground state, the lowest possible rung. This has profound consequences. In the ground state, quantum effects dominate. The uncertainty principle becomes directly observable. The wave nature of matter becomes undeniable. Particles that we normally think of as tiny billiard balls begin to spread out, to overlap, to lose their individual identity. This is where things get truly strange. At temperatures below about 2 Kelvin, certain substances undergo a phase transition unlike anything in ordinary experience. Helium, for instance, becomes a superfluid. A superfluid has zero viscosity. It can flow without any resistance whatsoever. It can climb up the walls of its container and escape. It can pass through gaps so small that normal liquids would be completely blocked. Superfluidity is a macroscopic quantum phenomenon. The atoms in a superfluid are all occupying the same quantum state, behaving as a single coherent wave rather than as individual particles. They become what physicists call a Bose-Einstein condensate. Now, CO molecules in interstellar clouds don't form Bose-Einstein condensates. The densities are far too low, and the temperatures, while frigid by any normal standard, are still too high for such exotic states. But they're close enough to the quantum realm that unusual effects begin to emerge. One of these effects is called quantum tunneling. At very low temperatures, particles don't have enough energy to overcome barriers through classical means. A molecule approaching a potential energy barrier, like a ball rolling toward a hill, would classically just bounce back if it didn't have enough energy to climb over. But quantum mechanics allows for a different outcome, because particles are also waves, and waves don't have sharp boundaries. There's a probability that the particle will simply appear on the other side of the barrier. It tunnels through rather than going over. At room temperature, this effect is negligible for most practical purposes. But at temperatures near absolute zero, tunneling becomes significant, even dominant. In cold CO clouds, quantum tunneling affects the rates of chemical reactions. Reactions that would be impossibly slow under classical physics can proceed through tunneling pathways. This has major implications for the chemistry of the interstellar medium. Consider the formation of molecular hydrogen, H2. Two hydrogen atoms colliding in space won't automatically stick together to form a molecule. The reaction actually releases energy, and that energy has to go somewhere. In the vacuum of space, there's nothing to absorb it, so the two atoms would just bounce apart. The solution nature found involves dust grains. Hydrogen atoms land on the surfaces of tiny dust particles, stick there, migrate across the surface, find each other, and react. The dust grain absorbs the excess energy. This process is called catalytic surface chemistry, and it's responsible for most of the molecular hydrogen in the universe. But here's where cold temperatures matter. At very low temperatures, atoms on dust grain surfaces don't have enough thermal energy to hop from site to site. Classical diffusion essentially stops. Yet molecular hydrogen continues to form. The answer is quantum tunneling. Hydrogen atoms tunnel between surface sites, moving through barriers that would classically trap them. The colder the dust grain, the more important tunneling becomes. This isn't just abstract physics. The molecular hydrogen formed through these processes goes on to form stars. Without quantum tunneling on cold dust grains, star formation would proceed very differently. The chemistry of the universe would be altered. You wouldn't be here to listen to this. Cold CO clouds are also laboratories for studying a phenomenon called line narrowing. When molecules emit radiation, the wavelength isn't perfectly precise. There's always some spread, some uncertainty. At higher temperatures, this spread is dominated by the Doppler effect. Molecules moving toward the observer emit slightly blue-shifted radiation. Those moving away emit red-shifted radiation. The random thermal motions smear out the line into a broad peak. But as temperature drops, thermal motions decrease and the Doppler broadening shrinks. Lines become narrower and narrower. In the coldest CO clouds, the emission lines are so narrow that we can measure velocities to precisions of a fraction of a meter per second. We can detect the gentle gravitational stirring caused by distant planets. We can see the slow collapse of clouds that will one day form stars. This precision reveals something unexpected about cold molecular clouds. They're not static. They're dynamic, complex, turbulent environments. Radio observations show that CO clouds contain supersonic flows, shock waves, rotating disks, collapsing cores, and expanding shells. The apparent stillness is an illusion created by the vast scales involved. A slow motion in these clouds might be traveling at several kilometers per second, which is supersonic in the cold gas, but looks stationary when you're observing from light years away. Let's talk about the structure of these clouds for a moment. Cold CO clouds aren't uniform blobs of gas. They have intricate filamentary structures. Observations with modern radio telescopes reveal networks of thin filaments, dense cores, and cavernous voids. The filaments are typically about 1/10 of a light year wide, but can stretch for dozens of light years. They look eerily like the web of neurons in a brain, or the structure of the cosmic web on much larger scales. Why filaments? The answer involves the interplay of gravity, turbulence, and magnetic fields. Magnetic fields thread through interstellar clouds, supported by the tiny fraction of atoms that are ionized. These fields resist compression in directions perpendicular to the field lines, but allow matter to flow freely along them. The result is that collapsing gas tends to form elongated structures aligned with the magnetic field. Turbulence adds another layer of complexity. Supersonic turbulent flows create shock waves where gas is compressed. These shocks also tend to produce filamentary structures. The interaction between magnetic fields and turbulence creates the intricate web we observe. Dense cores form where filaments intersect or where particularly strong compressions occur. These cores are the coldest, densest parts of the cloud. Temperatures can drop below 10 Kelvin. Densities can reach millions of molecules per cubic centimeter. That's still an incredibly hard vacuum by Earth standards, but it's dense enough for gravity to take hold. When a core becomes dense and cold enough, it begins to collapse under its own gravity. This is the birth of a star. The collapse doesn't happen smoothly. As gas falls inward, it spins faster, like a figure skater pulling in their arms. Angular momentum prevents the gas from falling directly onto the forming star. Instead, it spirals in, forming a disk. Jets of material shoot out along the rotation axis, punching through the surrounding cloud. All of this can be traced using CO observations. The molecule is like a spotlight illuminating the darkness, revealing the hidden processes of star formation. But cold CO clouds hold even stranger secrets. In the densest, coldest cores, something peculiar happens to the CO itself. It freezes out. At temperatures below about 20 Kelvin, in regions where the density exceeds roughly 10,000 molecules per cubic centimeter, CO molecules begin to stick to dust grains. They form icy mantles, mixed with water ice, carbon dioxide ice, and other frozen volatiles. The gas phase CO literally disappears. This creates a paradox. The very molecule we use to observe cold clouds vanishes in the coldest regions. Astronomers call this CO depletion, and it's a major challenge for understanding the innermost parts of star-forming cores. Other molecules become more useful tracers in these extreme environments. Nitrogen-bearing species like ammonia and N2H+ don't freeze out as readily and can be used to probe the densest, coldest gas. But even these have their limitations. The freeze-out of CO onto dust grains isn't just an observational inconvenience. It has chemical consequences. On the surfaces of dust grains, frozen molecules can undergo reactions that wouldn't occur in the gas phase. UV photons and cosmic rays provide energy to break bonds. Radicals form and react. Complex organic molecules are built up layer by layer. Laboratory experiments have shown that conditions mimicking cold interstellar dust grains can produce amino acids, the building blocks of proteins. They can create nucleobases, the components of DNA and RNA. The cold, dark hearts of molecular clouds may be factories for the precursors of life. This raises a profound question. Where did the chemical ingredients for life on Earth come from? Some portion almost certainly arrived on comets and asteroids, remnants from the solar system's formation. And those building blocks may have originated in the frigid darkness of a molecular cloud, built up over millions of years on microscopic grains of dust. We are quite literally children of the cold. Let me take you deeper into the physics of near absolute zero temperatures. At extremely low temperatures, the distinction between different types of particles becomes crucial. All particles fall into two categories based on a quantum property called spin. Fermions have half-integer spin values and obey the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. Electrons, protons, and neutrons are fermions. Bosons have integer spin values and have no such restriction. Multiple identical bosons can pile into the same quantum state. Photons and certain atoms are bosons. This distinction leads to dramatically different behavior at low temperatures. Fermions, forbidden from sharing states, must stack up into higher and higher energy levels even at absolute zero. This creates what's called the Fermi sea, a filled volume in momentum space. The pressure exerted by this stacking, called degeneracy pressure, prevents certain astronomical objects from collapsing. White dwarf stars are held up by electron degeneracy pressure. Neutron stars are supported by neutron degeneracy pressure. Bosons, in contrast, all want to fall into the lowest energy state. At high temperatures, thermal excitation spreads them out. But as temperature drops, more and more pile into the ground state. Below a critical temperature, a macroscopic fraction of the particles occupy the same quantum state, forming a Bose-Einstein condensate. They become a single quantum object on a macroscopic scale. CO molecules are actually bosons. The most common isotope, carbon, 12 oxygen, 16, has 0 nuclear spin. In principle, CO gas could form a Bose-Einstein condensate if cooled sufficiently at high enough density. In practice, interstellar CO is far too dilute and still too warm for this to occur. But the fact that CO is a boson has other consequences. The statistics governing how molecules distribute themselves among quantum states depends on whether they're fermions or bosons. For CO, Bose-Einstein statistics apply. This affects the populations of rotational energy levels, the intensities of emission lines, and the interpretation of temperature measurements. When we say a CO cloud has a temperature of 10 Kelvin, we usually mean the kinetic temperature related to the random velocities of molecules. But we can also define an excitation temperature based on the populations of quantum states. In thermodynamic equilibrium, these temperatures are the same. But in the tenuous interstellar medium, equilibrium isn't guaranteed. Molecules can absorb radiation from the cosmic microwave background, from nearby stars, or from other molecules. They can collide with hydrogen molecules, transferring energy. The balance between these processes determines the excitation state. In many cases, the excitation temperature is lower than the kinetic temperature. The molecules are underpopulated in excited states, cooler than their surroundings in a quantum sense. This leads to a phenomenon called subthermal excitation. CO molecules in diffuse clouds often show excitation temperatures close to the cosmic microwave background temperature of 2.7 Kelvin, even when the kinetic temperature is significantly higher. They're being pumped down by the cold bath of microwave photons that fills the universe. The cosmic microwave background itself is a remnant of the hot, dense early universe. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen. Light, which had been constantly scattering off free electrons, was suddenly free to travel. That light has been traveling ever since, stretched by the expansion of the universe from its original temperature of about 3,000 Kelvin down to 2.7 Kelvin today. This radiation fills all of space. Every cubic centimeter of the universe contains about 400 cosmic microwave background photons. Cold CO clouds are bathed in this radiation. They absorb it, emit it, reach equilibrium with it. The coldest temperature any object in the universe can naturally reach without active cooling is the temperature of this background radiation. Except there's a loophole. In the expanding universe, the cosmic microwave background is getting colder. It decreases by about 1 degree per billion years as the universe expands. A cold CO cloud today at 3 Kelvin is warmer than the same cloud will be in 1 billion years when the background is cooled further. Looking the other direction in time, the early universe was warmer. The cosmic microwave background was hotter. At a redshift of 1, about 8 billion years ago, the background temperature was about 5.4 Kelvin. At a redshift of 10, less than 1 billion years after the Big Bang, it was 30 Kelvin. At a redshift of 1,000, at the moment of recombination, it was 3,000 Kelvin. The coldest places in the universe today weren't always cold. They couldn't have been. The universe itself sets the floor. This has implications for the history of star formation. In the early universe, molecular clouds couldn't cool below the ambient temperature of the cosmic microwave background. Star formation may have proceeded differently. The minimum mass of stars that could form was likely higher. The cosmic microwave background provided a floor of thermal support that prevented the smallest clumps from collapsing. We can test this by observing distant galaxies at high redshift. The light we receive from them left billions of years ago, when the universe was younger and warmer. Observations of CO in these galaxies show higher excitation temperatures, consistent with a hotter cosmic microwave background. It's a beautiful consistency check on our understanding of cosmology. Now let's explore some of the more exotic physics that emerges at temperatures approaching absolute zero. At very low temperatures, the wave nature of particles becomes increasingly important. The de Broglie wavelength, which characterizes the quantum wave associated with any particle, grows larger as temperature drops. At room temperature, a CO molecule has a de Broglie wavelength of about 1/10 of an angstrom, much smaller than the size of the molecule itself. It behaves like a classical particle, but at 1 Kelvin, the de Broglie wavelength grows to about 10 angstroms. At a millikelvin, it's hundreds of angstroms. At nanokelvin temperatures achieved in laboratories, the de Broglie wavelength can exceed a micron. Particles become smeared out over distances visible under an optical microscope. When the de Broglie wavelength becomes comparable to the spacing between particles, quantum effects become unavoidable. Particles begin to overlap, to interfere, to lose their individual identity. This is the regime of quantum degeneracy. In cold CO clouds, the densities are too low for full quantum degeneracy. The average spacing between molecules is typically centimeters to meters, far larger than any quantum wavelength. But certain quantum effects still manifest. Consider the collision between two CO molecules at very low temperature. Classically, we'd model this as two billiard balls bouncing off each other. We'd calculate trajectories, impact parameters, energy transfers. At high temperatures, this works fine, but at low temperatures, the quantum nature of the collision becomes apparent. The molecules approach each other as waves, not particles. They interfere. The collision cross-section, which determines how likely two molecules are to interact, can differ dramatically from classical predictions. Certain quantum resonances can enhance collision rates. Others can suppress them. These quantum collision effects influence the chemistry of cold clouds. Reaction rates depend on how often molecules collide and with what energy. At low temperatures, quantum effects modify both. Tunneling allows reactions to proceed through classically forbidden pathways. Resonances enhance certain channels while suppressing others. The result is a chemistry unlike anything familiar from room temperature laboratories. Reactions that would be fast become slow. Reactions that should be impossible proceed efficiently. The molecular composition of cold clouds reflects this exotic quantum chemistry. One striking example is the deuterium fractionation observed in cold molecular clouds. Deuterium is the heavy isotope of hydrogen, with a nucleus containing 1 proton and 1 neutron instead of just a proton. In the overall universe, deuterium is about 100,000 times less abundant than ordinary hydrogen. It was produced in the Big Bang and has been slowly destroyed in stars ever since. In cold molecular clouds, however, Deuterium-bearing molecules are often much more abundant relative to their hydrogen-bearing counterparts than this ratio would suggest. Deuterated water, HDO, can be thousands of times more abundant relative to H2O than the cosmic deuterium ratio would predict. Doubly deuterated molecules, like D2O and ND3, are also enhanced. Why does this happen? The answer lies in quantum mechanics and the tiny difference in mass between hydrogen and deuterium. Consider the reaction between H3+ and HD, producing H2D+ and H2. At high temperatures, this reaction proceeds equally in both directions, maintaining equilibrium abundances. But at low temperatures, the small difference in zero-point energy between the products and reactants matters. Zero-point energy is the minimum energy a quantum system can have, even at absolute zero. It's a consequence of the uncertainty principle. You can't simultaneously know both the position and momentum of a particle with perfect precision. This irreducible uncertainty manifests as a minimum energy. Heavier isotopes have lower zero-point energies because they move more slowly. In the reaction above, the products, H2D++ H2, have slightly lower total zero-point energy than the reactants, H3++ HD. At temperatures above about 50 Kelvin, this energy difference is negligible compared to thermal energy, and the reaction proceeds equally in both directions. But at temperatures below about 30 Kelvin, the energy difference starts to matter. The reaction preferentially goes in the direction of lower zero-point energy, producing H2D+ at the expense of H3+. This is deuterium fractionation. The process cascades. H2D+ can react with HD to form D2H+. D2H+ can react with HD to form D3+. At temperatures below 10 Kelvin, these multiply deuterated species can become remarkably abundant. The deuterated molecules then transfer their deuterium to other species through subsequent reactions. CO can become DCO+. N2H+ becomes N2D+. Ammonia becomes NH2D, NHD2, and even ND3. Observationally, high deuteration is a signpost of extreme cold. When astronomers find molecular clouds with deuterium fractionation exceeding 1%, they know they're looking at gas colder than about 15 Kelvin. It's a cosmic thermometer based on quantum mechanics. The coldest known molecular cloud cores show deuterium fractionation exceeding 10% in some molecules. These are environments where temperatures have dropped below 7 Kelvin, where the chemistry is dominated by quantum effects, where we're approaching the floors set by the cosmic microwave background. What would it be like to exist in such an environment? First, let's be clear. You couldn't survive. Your body is roughly 300 Kelvin. Dropped into a 3 Kelvin environment, you would radiate heat away furiously. Every second, you'd lose energy equivalent to several hundred watts. Within minutes, your outer tissues would freeze. Within hours, you'd be a solid block at equilibrium with your surroundings. But suppose you could somehow observe without interacting. What would you perceive? The first thing you'd notice is the darkness. Cold CO clouds are opaque to visible light. The dust mixed with the gas blocks almost all starlight. In the densest cores, the visual extinction can exceed tens of magnitudes. That means less than 1 photon in 10 billion makes it through. Your eyes, adapted to earthly conditions, would see nothing but blackness. But if you could see in the radio, the infrared or millimeter wavelengths, the view would transform. You'd see glowing filaments of CO emission threading through the void. You'd see dense cores lighting up in ammonia and nitrogen hydride. You'd see the faint glow of dust grains, warm compared to the gas, radiating in the far infrared. The sound would be different too. Of course, space is a vacuum. There's no medium to carry sound waves in the traditional sense. But the gas itself supports pressure waves. At the incredibly low densities of molecular clouds, these waves travel slowly and have wavelengths stretching across light years. They're more like geological processes than sounds, but they're there. Turbulent motions, gravitational collapses, shock waves from supernova explosions all create pressure disturbances that propagate through the cold gas. Time would feel different. At 3 Kelvin, molecules move slowly. Chemical reactions crawl. A typical molecule might wait millions of years between collisions. The lifetime of a cold, dense core before it collapses to form a star is a few 100,000 years. That's long by human standards, but brief in cosmic terms. The universe is patient. It can wait. Let's discuss some of the specific environments where the coldest CO is found. One famous example is the Boomerang Nebula, located about 5,000 light-years from Earth in the constellation Centaurus. This is actually a protoplanetary nebula, a dying star shedding its outer layers. The central star has ejected a massive outflow of gas, expanding at about 600 kilometers per second. As this gas expands, it cools adiabatically. The Boomerang Nebula holds the record for the coldest known natural environment in the universe. Observations in 1995 using the Swedish ESO submillimeter telescope revealed that the outflowing gas has cooled to about 1 Kelvin. That's colder than the cosmic microwave background. How is this possible? Didn't I say that the cosmic microwave background sets a floor? The key is that the Boomerang Nebula's gas is still expanding. It's doing work against its surroundings, losing internal energy in the process. This adiabatic cooling temporarily drops the temperature below the ambient radiation field. The gas is absorbing cosmic microwave background photons, slowly warming back up, but the expansion is currently winning. This situation is temporary. Over thousands of years, the expansion will slow and the gas will equilibrate with the cosmic microwave background. The Boomerang Nebula's extreme cold is a transient phenomenon, a fleeting glimpse of temperatures even lower than the universe typically allows. The physics is similar to what happens in your refrigerator. A gas is compressed, allowed to cool by releasing heat, then expanded. The expansion drops the temperature below ambient. In the Boomerang Nebula, gravity provided the initial compression over the star's lifetime. The expansion is the star's dying gasp. More typical cold CO environments are found in dark clouds scattered throughout the galaxy. The Taurus molecular cloud, about 450 light-years away, is one of the nearest and best-studied star-forming regions. It contains dozens of dense cores with temperatures between 7 and 15 Kelvin. Young stars are forming in these cores right now. The Pipe Nebula in the constellation Ophiuchus is another famous dark cloud. It gets its name from its shape, resembling a smoking pipe in silhouette against the bright star clouds of the galactic center. The pipe contains numerous dense cores, some of which show evidence for the very earliest stages of gravitational collapse. The Serpens South Cluster, about 1,500 light-years distant, is a younger, more active star-forming region. Here, the cold gas is being actively disturbed by outflows from newly formed protostars. The interplay between cold, quiescent gas and energetic young stars creates a complex, dynamic environment. In all these regions, CO observations provide critical insights. The distribution of cold gas, its temperature structure, its velocity field, its chemical composition, all are revealed through the radio emission of this simple molecule. But CO isn't the only probe of cold gas. Let me introduce you to some of its cousins. Carbon monoxide has several isotopic variants. Besides the common carbon 12 oxygen 16 form, there's carbon 13 oxygen 16, carbon 12 oxygen 18, and carbon 13 oxygen 18. These isotopologues have slightly different masses and therefore slightly different energy levels. Their emission lines occur at slightly different frequencies. The rarer isotopologues are often better tracers of dense gas because they're optically thin. What does this mean? When light passes through a medium, it can be absorbed. If the medium is optically thick, so much absorption occurs that light from the back can't get through. We only see the surface. The common form of CO is often optically thick in dense clouds. We see emission from the cloud surface, but the interior is hidden. The rarer isotopologues, being less abundant, don't absorb as strongly. We can see through to the center of the cloud, getting a clearer picture of conditions there. Astronomers routinely observe multiple CO isotopologues to piece together the full picture. The ratio of emission between isotopologues tells us about optical depth, column density, and isotope ratios. Variations in isotope ratios across the galaxy reveal the history of stellar nucleosynthesis and chemical evolution. Other molecules probe different conditions. Ammonia, NH3, is an excellent thermometer because the populations of its quantum states are very sensitive to temperature. Carbon sulfide, CS, traces moderately dense gas. Hydrogen cyanide, HCN, and its isotopologues probe the densest regions where star formation is imminent. Formaldehyde, H2CO, has transitions that could determine both temperature and density independently. Each molecule is a specialized tool, sensitive to particular conditions. Combining observations of multiple species gives astronomers a three-dimensional view of the physical and chemical state of cold clouds. The chemistry of cold clouds is remarkably rich, considering the harsh conditions. Over 200 different molecules have been detected in interstellar space, ranging from simple diatomics like CO and CN to complex organics like ethyl formate, C2H5OCHO, and cyanopollenes with more than 10 carbon atoms. How can such complex molecules form in environments so cold that reactions should barely proceed? Part of the answer is time. Interstellar clouds exist for millions of years. Even slow reactions can proceed if you wait long enough. A rate coefficient of 10 to minus 17 cubic centimeters per second, incredibly slow by laboratory standards, translates to one reaction per molecule per million years at typical cloud densities. Over the lifetime of a cloud, that adds up. Part of the answer is surfaces. As we discussed earlier, dust-grained surfaces provide catalytic sites where atoms and molecules can meet and react. The surfaces accumulate icy mantles where even more complex chemistry occurs. When the ice eventually evaporates, either because the cloud warms during star formation or because it's sputtered off by shock waves, the products are released into the gas phase. Part of the answer is cosmic rays. High-energy particles from supernova explosions and other violent events penetrate even the densest clouds. When they collide with molecules, they ionize them, creating reactive species. The ions drive a whole cascade of ion-molecule reactions that can proceed even at very low temperatures because they don't require activation energy. The chemistry is still not fully understood. Every year, new molecules are discovered. Every year, chemical models are refined. The cold interstellar medium remains one of the most active areas of astrochemistry research. I want to take a moment to appreciate the telescopes that make all of this possible. Observing cold CO requires radio telescopes operating at millimeter and submillimeter wavelengths. These are challenging wavelengths to work with. Earth's atmosphere absorbs strongly at these frequencies, particularly due to water vapor. The best sites for submillimeter astronomy are high, dry, and cold. The summits of Mauna Kea in Hawaii, the Atacama Desert in Chile, the Antarctic Plateau. The Atacama Large Millimeter Array, known as ALMA, is perhaps the most powerful telescope for studying cold molecular gas. Located at 5,000 meters elevation in northern Chile, ALMA consists of 66 high-precision antennas that can be spread across distances up to 16 kilometers. By combining signals from all the antennas, ALMA achieves angular resolution better than 1/10 of an arcsecond, sharper than the Hubble Space Telescope at optical wavelengths. ALMA has revolutionized our understanding of cold molecular clouds. It can image the detailed structure of protoplanetary disks, the sites of planet formation. It can detect molecules and galaxies at the edge of the observable universe. It can probe the innermost regions of collapsing cores where stars are being born. Before ALMA, single-dish telescopes like the Institut de Radioastronomie Millimétrique, IRAM 30-meter telescope in Spain, the James Clerk Maxwell Telescope in Hawaii, and the Atacama Submillimeter Telescope experiment in Chile provided foundational observations. These instruments continue to contribute, particularly for mapping large areas of sky that ALMA's small field of view makes impractical. Space telescopes have also contributed. The Herschel Space Observatory, operating from 2009 to 2013, observed in the far infrared and submillimeter from an orbit beyond the Moon's distance. Free from atmospheric absorption, Herschel mapped cold dust throughout the galaxy with unprecedented sensitivity. It revealed the ubiquitous filamentary structure of molecular clouds and measured dust temperatures as low as 7 Kelvin. Future facilities will push further. The Origins Space Telescope, if selected for development, would observe the far infrared with sensitivity far exceeding Herschel's. The next generation Very Large Array would provide high-resolution imaging at centimeter wavelengths, probing dense gas with unprecedented clarity. The Atacama Large Aperture Submillimeter Telescope, at last, a proposed 50-meter single dish, would map large areas of sky at submillimeter wavelengths far faster than ALMA. Each new telescope opens new windows on the cold universe. Let me return to the physics for a moment. There's a concept I haven't fully explained yet: the competition between heating and cooling in molecular clouds. Clouds don't just passively radiate away their heat. They're constantly receiving energy from their surroundings. Cosmic rays deposit energy when they ionize molecules. Ultraviolet photons from distant stars penetrate the outer layers and heat the gas. Turbulent motions dissipate, converting kinetic energy to heat. Young stars embedded in the clouds pour out radiation and winds. The temperature of a cloud represents the balance between heating and cooling. If heating dominates, the cloud warms up. If cooling dominates, it cools down. Equilibrium is reached when the two are balanced. The primary cooling mechanism at low temperatures is line emission for molecules. CO is one of the most important coolants. When a CO molecule is excited by a collision, it can radiate away that energy as a photon. The photon escapes the cloud, carrying energy with it. This is how the cloud loses heat. The efficiency of CO cooling depends on several factors. First, there need to be collisions to excite the CO. At very low densities, collisions are rare and cooling is slow. Second, the emitted photons need to escape. If the cloud is optically thick, photons are reabsorbed before they can leave, and cooling is reduced. Third, the CO needs to be present in the gas phase. If it's frozen onto dust grains, it can't cool the gas. At high temperatures, other species become important coolants. Ionized carbon, C+, dominates cooling in the outer layers of clouds where UV photons penetrate. Neutral oxygen contributes in some conditions. Dust grains, heated by starlight, can either heat or cool the gas, depending on their temperature relative to the gas temperature. The detailed thermal balance of molecular cloud involves dozens of heating and cooling processes, all interacting in complex ways. Numerical simulations track these processes, solving the equations of radiative transfer alongside the equations of hydrodynamics and chemistry. These simulations reproduce many of the observed properties of cold clouds, giving us confidence that we understand the underlying physics. One key result from these simulations is that molecular clouds are thermally unstable over certain ranges of density and radiation field. Small perturbations grow, leading to the formation of cold, dense clumps embedded in warmer diffuse gas. This thermal instability may be one of the drivers of structure formation in the interstellar medium. Gravitational instability is the other major driver. When a region of gas becomes dense enough and cold enough, its self-gravity overcomes the internal pressure. It begins to collapse. The threshold for gravitational instability is given by the gene's mass, which depends on temperature and density. Lower temperatures mean smaller genes' masses. Cold clouds can fragment into smaller pieces than warm clouds. This is why temperature matters so much for star formation. In a warm cloud, only massive fragments can collapse, forming only massive stars. In a cold cloud, small fragments can collapse, forming low-mass stars as well. The distribution of stellar masses, called the initial mass function, is influenced by the temperature structure of the birth cloud. Understanding what controls cloud temperatures is therefore crucial for understanding star formation across the universe. Let's talk about what happens when cold clouds finally collapse to form stars. The process begins slowly. A dense core, perhaps a tenth of a light year across, and containing a few solar masses of gas, begins to contract. At first, the contraction is slow, limited by the time it takes gas to flow through the magnetic field. This phase can last 100,000 years or more. As the core contracts, its center becomes denser. Eventually, a protostar forms, a small, hot object at the center of the infalling envelope. The protostar grows by accreting material from its surroundings. But it can't accrete directly. Angular momentum sends the gas into orbit, forming a disk. The disk is a fascinating object in its own right. It's cold, typically 10 to 100 Kelvin in its outer parts, warming to over 1,000 Kelvin close to the star. CO observations trace the disk structure, revealing rotation curves that follow Kepler's laws. These disks are the birthplaces of planets. The young star also drives powerful outflows. Jets of ionized gas blast out along the rotation axis at hundreds of kilometers per second. Slower molecular winds sweep up the surrounding gas. These outflows inject energy and momentum into the parent cloud, eventually dispersing it. The whole process from cold, dense core to fully formed star takes a few million years. It's brief on cosmic timescales, but far too slow to watch in a human lifetime. We see the process by observing many different systems at different stages, assembling a composite picture like frames of a movie. Throughout all of this, CO remains our faithful guide. In the infalling envelope, we see broad absorption lines as cold gas falls toward us. In the disk, we see rotating emission tracing the orbital motion. In the outflows, we see high-velocity wings extending far from the systemic velocity. Each component tells part of the story. Now I want to explore something more speculative: the possibility of life in very cold environments. On Earth, we know life requires liquid water. The biochemistry we're familiar with operates in aqueous solution at temperatures between the freezing and boiling points of water. But could there be different biochemistries operating at very different temperatures? Theorists have speculated about life based on liquid ammonia, which remains liquid down to minus 77 degrees Celsius at standard pressure. Ammonia-based life could potentially operate on cold worlds like Titan, where surface temperatures are around minus 180 degrees Celsius. Titan actually has lakes and seas of liquid hydrocarbons, methane and ethane, which might also serve as solvents for exotic biochemistry. But what about temperatures near absolute zero? Could there be life in cold CO clouds? The honest answer is probably not, at least not as we understand life. The fundamental problem is kinetics. Chemical reactions slow down exponentially as temperature drops. At 3 Kelvin, reactions that occur in nanoseconds at room temperature would take longer than the age of the universe. Any metabolism based on chemical reactions would be impossibly slow. Quantum tunneling can help, but only for certain types of reactions. The light atoms involved in biological chemistry, like hydrogen, can tunnel efficiently. But the larger molecules of life, proteins and nucleic acids, are too massive for tunneling to significantly speed their reactions. There might be loopholes. If somehow the relevant chemistry could be arranged to proceed through strongly exothermic steps, released energy might locally drive reactions. If quantum coherence could be maintained over long times and large scales, perhaps quantum-enhanced catalysis could speed things up. These are speculative ideas with no experimental support, but they remind us not to be too dogmatic about what's possible. Another possibility is that cold CO clouds could harbor extremely patient life. A metabolism operating 1,000,000 times slower than Earth life would still get things done eventually, just on geological rather than biological timescales. 1,000,000 years for a single thought. 1,000,000,000 years for a conversation. It's hard to imagine what such existence would be like, but it's not strictly forbidden by physics. More practically, cold molecular clouds are probably important for seeding the universe with prebiotic chemistry. The complex organic molecules formed on cold dust grains, delivered to young planets by comets and asteroids, may provide the raw materials for life's origin. In this sense, cold clouds are the cosmic kitchens where the ingredients for life are prepared. The question of life in the universe remains open. We've detected no signals, no biosignatures, no indications of intelligent activity beyond Earth. But the search continues, and understanding the environments where life might arise, including the coldest reaches of molecular clouds, is part of that search. Let's shift to the role of cold molecular gas in galaxies as a whole. Every galaxy contains interstellar gas, though the amount varies enormously. Spiral galaxies like the Milky Way are rich in gas, with several percent of their mass in atomic and molecular hydrogen. Elliptical galaxies have much less gas, having converted most of it to stars long ago. Irregular and dwarf galaxies span a wide range. The molecular gas, traced by CO, is concentrated in the disks of spiral galaxies. It follows the spiral arms, concentrating in the regions of strongest gravitational compression. The spiral pattern triggers the formation of giant molecular clouds, which in turn form stars, which in turn illuminate the spiral arms. It's a self-reinforcing cycle. At the centers of many galaxies, molecular gas concentrates in nuclear rings and bars. Some of this gas feeds central black holes, powering active galactic nuclei. Some forms intense bursts of star formation, creating nuclear starbursts. The physics connecting cold gas to black hole feeding and nuclear activity is an active area of research. The total amount of molecular gas in a galaxy correlates with its star formation rate. Galaxies with more gas form more stars. This correlation, called the Kennicutt-Schmidt law, holds across many orders of magnitude in gas density and star formation rate. It tells us that star formation is fundamentally limited by the availability of cold, dense gas. But the efficiency of star formation varies. In quiescent disks like the Milky Way, only about 1% of the molecular gas is converted to stars every 100 million years. In starburst galaxies, the efficiency can be 10 times higher. Something besides just the presence of gas must control the rate of conversion. That something is likely a combination of factors: the turbulent state of the gas, the strength of feedback from young stars, the role of magnetic fields, and the overall gravitational potential. Disentangling these factors is one of the major challenges in understanding galaxy evolution. CO observations in distant galaxies have revealed something remarkable. In the early universe, galaxies contained much more molecular gas than similar galaxies today. At a redshift of 2, about 10 billion years ago, typical star-forming galaxies had gas fractions of 50% or more, compared to 10% or less today. The universe has been using up its gas reserves. This gas depletion helps explain the decline of cosmic star formation. The star formation rate density of the universe peaked around redshift 2 and has been declining ever since. We're living in the twilight of the star-forming era. Eventually, the gas will run out, star formation will cease, and the universe will grow dark. That's a long way in the future. Trillions of years. Nothing to worry about today. But it's humbling to realize that our active, star-forming universe is a temporary phase, not the permanent state of things. Let me tell you about some of the strangest cold molecular environments in the universe. Titan, the largest moon of Saturn, has a thick nitrogen atmosphere and surface temperatures around 94 Kelvin. It's not as cold as interstellar space, but it's cold enough for methane to exist as a liquid. Methane clouds form in Titan's atmosphere. Methane rain falls on the surface. Rivers and lakes of liquid methane of the landscape. Titan doesn't have significant CO in its atmosphere, but it does have complex organic chemistry. Ultraviolet light and energetic particles break apart nitrogen and methane, initiating chains of reactions that produce a smog of organic hazes. These particles settle to the surface, building up organic deposits over billions of years. In some ways, Titan is a cold analog of early Earth. The organic chemistry occurring there may be similar to the prebiotic chemistry that preceded life on our planet. But the cold temperatures slow everything down. What might have taken thousands of years on warm Earth could take billions of years on cold Titan. Triton, the largest moon of Neptune, is even colder, around 38 Kelvin. Its surface is covered with frozen nitrogen, with traces of frozen carbon monoxide, carbon dioxide, and methane. Geysers erupt from the surface, spewing nitrogen gas into the thin atmosphere. Triton is thought to be a captured Kuiper belt object, a frozen world from the outer reaches of the solar system. Pluto and other Kuiper belt objects share Triton's frozen character. The New Horizons mission revealed Pluto's complex surface geology, including mountains of water ice, plains of nitrogen ice, and glaciers of frozen carbon monoxide. The surface temperature is about 40 Kelvin. It's a frozen world, but not a dead world. Internal heat may still drive geological activity. Comets are even colder in their distant orbits. In the Oort cloud, trillions of icy bodies orbit the Sun at distances of tens of thousands of astronomical units. Surface temperatures, there are just a few Kelvin above the cosmic microwave background. These are the coldest objects bound to our solar system. When comets fall inward, they warm up. Frozen volatiles sublimate, forming the spectacular tales that have amazed humans throughout history. The gas released from comets has been studied spectroscopically, revealing a rich inventory of molecules including CO, carbon dioxide, water, methanol, formaldehyde, hydrogen cyanide, and many others. Comets are frozen samples of the solar nebula, preserving the chemical composition of the cloud that formed the Sun and planets. The ice locked in comets may have been inherited from the cold molecular cloud that preceded the solar system. If so, comets provide a direct link between the chemistry of interstellar space and the chemistry of our planetary system. I want to spend some time discussing the observational techniques used to measure temperatures in cold molecular gas. The most direct method uses the relative intensities of different rotational transitions. CO molecules can rotate at different rates, corresponding to different quantum states labeled by the rotational quantum number J. The J equals 1 to 0 transition produces the familiar 2.6 millimeter line. Higher transitions, like J equals 2 to 1 at 1.3 millimeters or J equals 3 to 2 at 0.87 millimeters, require more energy to excite. At higher temperatures, molecules have enough collisional energy to populate higher J states, and the high J transitions are strong. At lower temperatures, only the lowest J states are populated and high J lines are weak. By measuring the ratio of line intensities, astronomers can infer the excitation temperature. This method has caveats. The populations depend not just on temperature, but on density. At low densities, collisions are too rare to maintain thermal equilibrium, and the populations don't reflect the kinetic temperature. The inferred excitation temperature is then a lower limit. Detailed models are needed to interpret the observations. Ammonia provides a cleaner temperature measurement. The ammonia molecule has a particular quantum mechanical property called inversion. The nitrogen atom can tunnel back and forth through the plane of the three hydrogen atoms, creating two slightly different energy states. The energy difference between these inversion states depends sensitively on temperature. By measuring the relative intensities of different ammonia inversion transitions, astronomers can determine the gas temperature with good precision, especially in the range from 10 to 100 Kelvin. Ammonia is therefore a workhorse for temperature measurements in cold cores. Other molecules have their own temperature-sensitive transitions. Formaldehyde has a pair of lines whose ratio is a good thermometer. Methanol has complex internal rotation that makes it sensitive to temperature. Each molecule requires specific models to interpret, but together they provide a comprehensive picture. Dust temperatures can be measured independently from the spectral energy distribution. Cold dust emits thermal radiation with a spectrum that peaks at far infrared wavelengths. By measuring the brightness at multiple wavelengths, astronomers can fit a modified blackbody curve and determine the temperature. Interestingly, dust and gas temperatures aren't always the same. In the outer parts of clouds, where densities are low, dust and gas are thermally decoupled. The dust, absorbing starlight and radiating in the infrared, reaches an equilibrium temperature set by the radiation field. The gas, heated by cosmic rays and cooled by line emission, reaches a different equilibrium. Deep in cloud cores, where densities are high, collisions between gas molecules and dust grains become frequent enough to equilibrate the two temperatures. Here, dust and gas are coupled, and measuring either gives the true temperature. The temperature structure of a molecular cloud is therefore complex. Warm dust in the outer layers, cold gas in the interiors, temperature gradients from edge to center, heating by embedded protostars, cooling by efficient line emission. It's a three-dimensional tapestry that we're only beginning to unravel with modern observations. Let me touch on the connection between cold gas and dark matter. Dark matter makes up about 85% of the matter in the universe, but it doesn't interact with light or with ordinary matter except through gravity. We can't see it directly. We infer its presence from its gravitational effects on visible matter. In galaxies, dark matter forms extended halos that envelope the visible disk. The gravitational potential of the dark matter halo determines the rotation curve of the galaxy. It also influences the formation and evolution of molecular clouds. Cold gas clouds feel the gravitational tug of dark matter. In the outer parts of galaxies, where the dark matter halo dominates, cloud dynamics are governed by the dark matter potential. Clouds orbit the galactic center on paths determined by the combined gravity of dark matter, stars, and gas. On smaller scales, within individual clouds, dark matter plays little role. The density of dark matter in the solar neighborhood is about 1 million times less than the density of a typical molecular cloud. Gravity within clouds is dominated by the gas itself, not by dark matter. But there are speculative ideas connecting cold gas to dark matter more intimately. Some models of dark matter suggest it could clump on small scales, forming mini halos that might concentrate gas. Other models propose interactions between dark matter and ordinary matter that could create observable effects in the coldest environments. None of these ideas have been confirmed. Dark matter remains one of the great mysteries of physics, but studying cold molecular gas pushes our understanding of matter to its limits, and who knows what connections might emerge. I want to discuss the future of cold molecular gas in the universe. As I mentioned earlier, galaxies are using up their gas reserves. Star formation converts gas to stars, and the process is irreversible. Once hydrogen is fused to helium in stellar cores, it can't be converted back to cold molecular gas. Gas can be recycled to some extent, Stellar winds return processed material to the interstellar medium. Supernova explosions disperse heavy elements throughout galaxies. Planetary nebulae contribute puffs of enriched gas. But the recycling isn't perfect. Some mass is locked forever in white dwarfs, neutron stars, and black holes. The infall of fresh gas from the intergalactic medium can replenish galactic reserves. Galaxies continue to accrete gas from their surroundings, particularly from cosmic filaments that channel material toward galactic halos. But even this infall is decreasing as the universe expands and dilutes the intergalactic medium. Over trillions of years, galaxies will run out of gas. Star formation will cease. The stellar populations will age, dimming as the most massive stars die and are not replaced. Eventually, only red dwarfs will remain, slowly burning through their hydrogen fuel over timescales of trillions of years. In this far future, cold molecular clouds will be rare or absent. The carbon monoxide that allows us to study these clouds will be locked in stellar remnants or dispersed to undetectable densities. The universe will be a colder, darker, emptier place. But that's not the end of the story. Even in the far future, random fluctuations can concentrate matter. Dark matter halos can continue to form from gravitational instability. Given enough time, even incredibly improbable configurations will eventually occur. The universe has eternity to wait. Some cosmologists have speculated about a far future stelliferous era when new structures form from the dregs of the old. Others see an endless dark era of slowly decaying remnants. The ultimate fate of the universe depends on physics we don't yet understand. The nature of dark energy, the stability of the vacuum, the possibility of new phase transitions. What we do know is that right now, in this cosmic moment, we have cold molecular clouds. We have star formation. We have the chemical richness that allows complex structures, including life, to exist. We should appreciate this fleeting moment of cosmic fecundity. Let me bring things back to the specific physics of cold CO. Carbon monoxide has a dipole moment of about 0.1 dBi, quite small compared to molecules like water, 1.85 dBi, or ammonia, 1.47 dBi. This small dipole moment means CO interacts weakly with electric fields and radiates relatively weakly in its rotational transitions. The weakness is actually an advantage for tracing mass. Strongly radiating molecules like water or ammonia become optically thick at relatively low column densities. Their emission saturates, and we can't see deep into clouds. CO's weaker radiation remains optically thin to higher column densities, allowing us to trace gas to greater depths. The common isotope of CO has rotational energy levels spaced by about 5.5 Kelvin, with the first excited state, J equals 1, lying 5.5 Kelvin above the ground state, J equals 0. This is why CO is such a good tracer of cold gas. At temperatures of 10 to 20 Kelvin, the J equals 1 state is well populated, and the 2.6 millimeter transition is strong. At much lower temperatures, the J equals 1 state becomes depopulated and a line weakens. The rare isotope carbon, 13CO, has slightly different level spacings due to its different reduced mass. This shifts its emission lines to different frequencies, allowing isotopic studies. The ratio of carbon, 12CO, to carbon, 13CO, varies across the galaxy, reflecting differences in stellar nucleosynthesis history. Carbon monoxide is destroyed by ultraviolet radiation. Photons with wavelengths below about 1,100 angstroms can dissociate the molecule, breaking it apart into separate carbon and oxygen atoms. This happens in the outer layers of clouds, where UV from stars can penetrate. Deeper inside, the UV is absorbed by dust and by the CO itself, creating a shielded region where CO can survive. This self-shielding leads to a layered structure. At the edge of a cloud, hydrogen is atomic, Hi, carbon is ionized, C+, and oxygen is atomic O. Moving inward, hydrogen becomes molecular, H2, first because it self-shields more efficiently. Then CO forms once the UV is sufficiently attenuated. The CO bright region is typically smaller than the H2 rich region. This has implications for using CO to trace total molecular gas mass. If we just measure CO emission, we might miss some molecular hydrogen in the outer layers where CO is dissociated. Astronomers apply conversion factors to estimate total mass from CO luminosity, but these factors are uncertain and may vary with environment. At very low metallicities, where heavy elements like carbon and oxygen are scarce, CO becomes even less reliable as a mass tracer. Low metallicity galaxies may have significant molecular gas that's invisible in CO. Alternative tracers, like neutral carbon, Ci, or ionized carbon, Ci, become important in these environments. This is an active area of research. Understanding the CO to H2 conversion factor, called enigmatic CO, across different environments is crucial for measuring gas masses in galaxies near and far. Let me describe some cutting-edge observations that are pushing our understanding of cold CO. ALMA has imaged protoplanetary disks with stunning resolution, revealing gaps and rings in the dust distribution that may indicate the presence of forming planets. CO observations of these disks show the gas component, often more extended than the dust. In some cases, the CO appears to be depleted, frozen out onto dust grains, or perhaps incorporated into planetesimals. Observations of CO isotopes in these disks reveal the chemical processing occurring during planet formation. Different isotopes fractionate, meaning their relative abundances change due to differences in reaction rates. This fractionation is recorded in the bodies that form, providing a chemical fingerprint of their origin. ALMA has also detected CO in the atmospheres of exoplanets. When a planet transits in front of its star, some starlight passes through the planet's atmosphere, picking up spectral signatures of atmospheric gases. CO has been detected in the atmospheres of hot Jupiters, gas giants orbiting close to their stars. These detections reveal the composition and temperature structure of alien atmospheres. At the other extreme of scale, ALMA has mapped CO in galaxies at redshift greater than 6, less than 1 billion years after the Big Bang. These observations show that massive galaxies in the early universe already contain substantial molecular gas reservoirs. Star formation was occurring vigorously, building up the stellar populations we see in local elliptical galaxies today. The detection of CO at high redshift requires looking for the emission lines at wavelengths shifted by cosmic expansion. The J equals 2-1 line of CO at redshift 6 appears at a wavelength of about 2 millimeters within ALMA's range. Higher J lines are often easier to detect at very high redshifts because they're shifted into more accessible bands. These high redshift observations are challenging. The sources are faint, requiring many hours of integration. The angular sizes are small, demanding high spatial resolution. But the payoff is immense. a window into galaxy formation in the early universe, when the first stars and black holes were assembling. Closer to home, CO observations have mapped the three-dimensional structure of local molecular clouds using velocity information. Every CO line has a slight Doppler shift, depending on whether the emitting gas is moving toward or away from us. By measuring the spectrum at each position, astronomers can separate emission from different velocities and thus different distances along the line of sight. This technique reveals that molecular clouds are incredibly complex. Filaments twist and turn in 3 dimensions. Velocity gradients suggest rotation, infall, or turbulence. Shells and bubbles indicate past supernova explosions or stellar wind activity. The picture that emerges is far from the simple, static cloud models of textbooks. I should mention the connection to the study of the cosmic microwave background. The CMB is the oldest light in the universe, emitted when the cosmos was just 380,000 years old. Observations of tiny temperature fluctuations in the CMB have revolutionized cosmology, allowing precise measurements of the age, composition, and geometry of the universe. But the CMB passes through intervening matter on its way to our telescopes. Cold CO clouds can absorb CMB photons, leaving slight imprints on the observed spectrum. This effect, called the Sunyaev-Zel'dovich effect for hot gas in galaxy clusters, has a cold counterpart for molecular clouds. In most cases, the effect is too small to measure. Molecular clouds are too sparse and too low in contrast against the CMB. But in principle, the presence of cold gas modifies the CMB spectrum, adding tiny fluctuations on small angular scales. More importantly, when we observe CO emission from cold clouds, we're seeing that emission against the CMB background. The CMB provides a reference temperature. Clouds that are colder than the CMB appear in absorption. Clouds that are warmer appear in emission. This is how the Boomerang Nebula was discovered to be colder than the CMB. It appeared as a shadow against the uniform CMB glow. The interplay between molecular clouds and the CMB is a reminder that everything in the universe is connected. Life from the beginning of time interacts with gas formed billions of years later. We observe the combined signal, unraveling the layers to understand each component. I want to return to the human perspective. What does all of this mean for us? The cold CO clouds scattered throughout our galaxy are the raw material for future solar systems. The cloud that formed our sun 4.5 billion years ago was probably similar to the clouds we observe today. It was cold, perhaps 10 to 20 Kelvin. It contained CO and other molecules. It collapsed, formed a disk, gave birth to planets. We're made of material that was once part of such a cloud. The carbon in our bodies was forged in ancient stars and recycled through interstellar space. The oxygen we breathe was synthesized in stellar cores and expelled in supernova explosions. These atoms drifted through cold molecular clouds, froze onto dust grains, were incorporated into icy planetesimals, and eventually found their way to Earth. When we study cold CO clouds, we're studying our own origins. We're tracing the path from primordial hydrogen to complex life. We're understanding the cosmic processes that made our existence possible. This is why astronomy matters. Not for practical applications, though those exist. Not for national prestige, though that drives funding. But for understanding our place in the universe. For recognizing that we are not separate from the cosmos, but part of it, made of its substance, governed by its laws, participants in its unfolding story. The cold between the stars once seemed empty, lifeless, irrelevant to human concerns. Now we know it's a crucible of chemistry, a factory of molecules, a nursery of stars. The cold is not nothing. It's the womb of everything. As our technology improves, we'll learn more. We'll map the detailed structure of molecular clouds with better resolution. We'll identify more complex molecules, perhaps including direct precursors of life. We'll understand the physics connecting turbulence, magnetic fields, and gravity in exquisite detail. We'll watch star formation in real time, tracking changes over human lifetimes in the nearest clouds. Perhaps we'll discover surprises. Physics has a way of confounding expectations. The quantum behavior of ultra-cold matter has already revealed phenomena like superfluidity and Bose-Einstein condensation that nobody anticipated before quantum mechanics was developed. What other surprises lurk in the coldest reaches of the universe? Perhaps we'll find that the conditions for life are more common than we thought, that the cosmic chemistry produces biological precursors ubiquitously. Perhaps we'll find signs of life itself in our solar system or beyond. The search continues, guided by our understanding of the environments where life might emerge. Or perhaps we'll learn that Earth is rare, that the chain of events leading from cold gas to intelligent life is so improbable that we're alone in the observable universe. That would be a different kind of knowledge, humbling and isolating, but knowledge nonetheless. Either way, the study of cold CO clouds connects us to the largest questions. Where do we come from? What are we made of? Where are we going? Are we alone? Science can't answer all of these questions, but it illuminates them. It replaces mythology with measurement, speculation with observation, fear with understanding. The next time you look up at the night sky, remember that between those stars lies darkness. And in that darkness, cold beyond imagination, molecules drift and collide and radiate. Chemistry happens on timescales of millions of years. Stars are born and die, and somehow, through processes we're still unraveling, you emerged. A creature of warmth and light, looking back at the cold and dark from which you came. That's the story of cold CO clouds. Not just physics, not just astronomy, but the story of matter becoming aware of itself. The story of the universe looking back at the universe and asking, why? How? What next?